All right. All right, cool. All right. So that was our first example for integral curves, right? So what I'm going to do, I'm going to give a hard example now. So example 2 here, and again, these are all from probably your problem papers or problem sets. So here, we know that the integral curve is, or the gradient function is dy by dt is equal to 1 over 2 root t and passes through 2 root 2. So I can give you the chance to actually like meds it first and then like quick minute for meds it, and then we look at how we solve the question afterwards. So it passes through 2 root 2. So maybe I should write that better. All right, so let's actually make this now. Ready? So to do this, we have to integrate it, right? So let's do the formal solution again. So solution here, ready? So to integrate something like this, what we're going to do, we're going to start by separating the variables. So separating the variables, I'm going to have that dy is going to be equal to 1 over 2. No, Medzino, this is root 2 in the denominator. Root of any variable, so root of t rather, is just t to the half, right? Now, when I carry it to the numerator, it's just going to be t to the minus a half. So I'm carrying it to the numerator because I want to actually integrate it, and it's much better if it's in the numerator. So t to the minus half there, and I'm going to have dt. Now, when I integrate both sides, the integral of dy is going to be equal to the integral of t to the minus a half over 2 dt. Now, remember when you integrate dy, there's always a 1 here. So when I integrate, it's just going to give me y. You don't have to write the c1. Really and truly don't have to. You can only write it over here. So when I integrate t to the minus a half, remember, integrating, you add 1 to the power. So t to the minus a half plus 1 is going to give me a half. So t to the half now. Remember that it's over 2. Then what you do now, guys, you're going to divide by the new power. But when you're dividing by a half, right, it's the same as multiplying by 2. So simply what we'll do is multiply, I'll use a dot to multiply by 2, right? And then no, remember, don't leave off your constant of integration. Now what you realize is that this curve just simplifies to give us that y is equal to, the 2's will cancel here, right? T to the half, as I did demonstrate over here, is just root of t. So y is equal to the root of t plus c. Now, we know that the curve passes through, so we know that the curve passes through 2 root 2. The curve passes through 2 root 2. So 2 root 2. So use this information now to substitute it in. So I know that this is x, and this is t rather, and this is y, right? So when I substitute them in now, I get that the y value is root 2. So root 2 is equal to, the t value here is 2, so that's going to give me the root of 2 plus c. When I carry this root of 2 over here, it becomes root 2 minus root 2 is equal to c. We now find that c is equal to 0. So therefore, the integral curve is simply y is equal to root of t. Because we found c to be 0, so substitute 0 here, we get that y is equal to root t. So basically what I hope I would do with these two examples is demonstrate how you'd find an integral curve from the given information. All right, so I hope that example is clear, and let's move forward before we run out of time. All right, now what we're going to do, earlier I did demonstrate some of the integral properties by using some basic integrals, right? That's fine. That's the start as to where anybody would normally start off with integration. But we have a lot of other integral properties and rules that you guys must pay attention to. So in particular, there is an integration, there's a chain rule for integration, there is some quotient rule, there's a bag of stuff that you can use. But what I'd want you to most importantly remember is that all of these rules that I'm about to tell you are all derived from substitution. So if you were supposed to do substitution, they'll come back to give you the same answer. But once you know the results, then the results are very useful. So what I'm going to be looking at are some useful integral results. Useful integral results, right? The first one is going to be, all right, so I'm not so sure if the video will disconnect, but if the video disconnects, please just join back, just literally link back after it's done, right? But, so let's look at some useful integral results, ready? So the first result is, let me just write it as result 1, or property 1, or whatever you want to call it. So here we're saying that when I have a quotient, right, with the differential of the function in the numerator and the function in the denominator, and I'm differentiating with respect to x, then the result is just going to be what is the ln mod of fx, what's in the denominator, plus t. So this here is the first result that we're going to be looking at. It's very useful. In fact, we use it a lot in actuarial practice, a whole lot in actuarial practice, that it would make sense that you guys know it. Ready? So let's look at some example using this result here. Don't have much, so let's just work through them. Ready? So the first example that I'd like to use here, let's say example 1. All right, so what is the integral of 4x over 2x squared plus 3 dx? So usually to have you be able to pick it up, what I'll do is define f of x, right? So what I'm going to say here is let f of x be equal to 2x squared plus 3, right? Then it implies to me that f prime of x, which is the differential, when I differentiate this expression here, it's just going to give me 4x. Now what do you realize? I have the differential in the numerator, I have the function in the denominator. So whenever that is the case, the integral here will just give me ln of what's in the denominator plus c. So right away, if you were able to pick up this property, you would know by just simply writing this line here, therefore, the integral of 4x over 2x squared plus 3 is simply going to be equal to ln mod, do not leave off the mod, of 2x squared plus 3 plus c. For this particular case, the mod is not needed, but I doubt that you will remember when it's needed and when it's not needed. So just always put it there. All right. So always put your mod. In some cases, it's not needed because the number is guaranteed to be positive. But I don't want Johnny with that kind of analysis. So always write it to be safe. All right. So that was our first example. It was a very easy example, but the others are not going to be so easy. All right. So again, let me just write the property up here. So the property is when I have the differential in the numerator and the function in the denominator and I'm integrating, answer is just equal to ln mod of the function in the denominator plus c. All right. So let's look at one example that's probably going to be a little bit of a trick. Ready? So here I have the integral of 1 over x ln x. Can anybody think of how you'd solve something like this? dx. So here's how it makes a lot more sense. Ready? If I have a fraction, probably this will demonstrate it better. So if I have a fraction a over b, right? And I'm all dividing that by c, cool? Then we know in mathematics, it would reduce to give us something as a over bc. Cool. So what I'm doing here is I'm demonstrating how we're going to break this up. So I can move between these two results. So with 1 over x ln x, I can write it as 1 over x divided by ln x, and I'll be integrating this here with dx. Now, if you realize, we're going to say, let f of x equals ln x, right? If you remember from probably econ 1003, f prime of x, or the differential of ln x, would be 1 over x. So you realize now that I have a function in the denominator, and I have its differential in the numerator. When that's the case, it tells me that therefore 1 over x ln x is just dx is simply just going to be ln mod of what's in the denominator, ln of x mod plus c. Now I know that you probably be wondering, but how am I going to have ln of ln x? It's very much possible. So you're just taking the value of ln x and you're plugging it into another ln function. It's very much possible, right? So that's how you do that question. So again, you have to be able to pick up the different forms and the different results. So we're exploring the current result that says the integral, the differential of a function over the function is equal to ln mod of the function plus c. So let's look at an even harder example. So we're accelerating in difficulty level here. So let's look at example 3. So here with example 3, I want to show you how you can manipulate stuff. So I have e to the 2x here, and I have 1 plus e to the 2x in the denominator, and I'm integrating with respect to dx. So here, you probably haven't picked up that you can use the property because it's not so straightforward, right? So what I'm going to do, I'm going to let f of x equal the denominator. So when I do that, I'm going to get 1 plus e to the 2x. Now, when I differentiate this, I'm going to get that f prime of x. When I differentiate when I differentiate 1, that gives me naught, which is 0. When I differentiate e to the 2x, it's going to give me 2e to the 2x, right? Now you realize that in the current numerator, we only have e to the 2x. We needed to say that it is going to be 2e to the 2x. How can I change it to n? How can I change it to achieve that property? Well, what you can do, ready, is manipulate it. So we're going to manipulate e to the 2x over 1 plus e to the 2x so that it gives us the result that we want.